all over Tamil Nadu. We conduct various programs from primary classes themselves and up to school and colleges, middle school and colleges. We even run a magazine for primary students up to 8th standard to live in Tamil, and also another one in English for middle school and even some college students called Janta Manta. So these are some of the activities we have been doing. We also conduct some children's science congress programs where students, young students, take part in making their projects and making it visible. And we have been involved in environmental issues, various other questions. And I don't want to get into too much of a thing. Around 2018, we decided we will have this popular science lectures organized, and every month is one meeting. Maybe nowadays it is 2 meetings. We've been holding it in few places. One is thanks to Anna Centenary Library. We hold it in Anna Library. We also hold it in Institute of Mathematical Sciences, which is my institute where I'm retired from. There we also hold IIT Madras and Madras University and a couple of Madras Christian College, etc. We have been doing it in several places like that. So this is on, even though Tamil Nadu Science Forum tries to arrange talks in Tamil, we also don't want to be too rigid, want to take science in simplest possible language in English also, because many of the college students may be preferably attending these things more. With this in focus, we have been doing it from 2018, and unfortunately, I was the first to speak again, and it was held in the Anna Library at the ground floor, and thanks to all sections of, because it was the first time we held, thanks to all sections of students, we had about 300 students. So COVID did affect us because we had to shift to online mode, and we shifted to online mode where several lectures were organized every month, even during COVID, and a lot of interesting people spoke, and the list is probably available everywhere. I think this is the 82nd lecture. And the good thing about COVID is it gave the possibility of taking it to all over Tamil Nadu. In fact, now YouTube is on, and also Zoom is on. So people are listening to me, and they will also listen to the speakers. And the good thing is that it can reach. And the bad thing is when 300 students were attending in the initial thing, now many of the people, even in Chennai city, think that, okay, why should I come? I can listen to YouTube or this thing, which is fine. It is their choice because they have to do it. But the only thing is the people who come here, they can interact with the speakers much more than who listen to from other places. We do encourage question answer session, which normally used to go for 1 hour. But I don't know how far we can go, we'll see. And people do ask some questions from YouTube also. So this is the status. We have been successfully conducting this program, and I must apologize for all the people standing because at least some more chairs will be coming, I hope. With that, we have to move on for the talks. I don't want to delay the talks. There are 2 speakers. Dr. Sitabrah, my colleague actually, Institute of Mathematical Sciences. I know what she has been doing right from the beginning. So the moment I heard the Nobel thing, I called him. The first thing I did was to call him, and he was all the more willing to talk to us to come for this thing because he actually was working on this model of Hopfield. Hopfield model was his first kind of work. So he has been doing a lot of work. He works originally he was a physicist. He somehow went to computational biology. Just again,
I'm still a physicist.
Okay, so this is the way in which physics and biology and computers, everything get merged in some new format. which is making the whole program interesting. So next is Ravindra. He will be the speaker. He will speak for about 30 minutes, and he will continue with the artificial intelligence and what is happening, what physics gave and what is now people are doing, and it's mind-boggling. And if you are not familiar with both, particularly artificial intelligence, next 10 years, I must tell you, is going to be so fast that it is going to change the way we interact in the society, etc. So better be aware of what is happening. There are good things, there are bad things. So we have to be careful. Now, let me leave the floor to the first speaker, Dr. Sitabrah Sinha, and producer.
Thank you, TRG. So it's a pleasure. The call mic should work, right? Oh, it's on the Zoom. Okay. Okay, so first of all, thank you so much to TNSF for asking me to give this talk. As TRG said, my first ever research paper was on Hopfield model. So, it's a pleasure to talk about the work of Hopfield, which initially also inspired me to get into my scientific research. And just to give you a map of how we are going to go, okay, for some strange reason. Let me see, it should work. No? No. Oh, yeah, just click on it. Yeah, okay, great. So this is like a potted map of AI, or the history of AI, how we have gone to this deep learning. It's adapted from an image by Fabio Vasquez. And you will see that he kind of gives the highlights or the milestones of this road to AI. Now, it turns out that when Ravindra and I were discussing how we will divide the talk amongst ourselves, I said, okay, I'll talk about the physics, you talk about the AI part, but it turns out that there's also a very nice chronological divide. So I'll be talking about the time from the pre-1940s to essentially 1985. And yeah, that's fine, thanks. And Ravindran will kind of talk about the post-85 development, if I'm not mistaken. Well, I mean, he's doing like this, but anyway, we'll see. All right. Okay. So, so as you will notice, the milestones here is what happened before the 1940s, which I call kind of the prehistory. And then the way I see AI really started off from a landmark paper published in 1943, which essentially gave us this idea of neurons as switches. Okay, so instead of viewing neurons as something extremely complicated biological cell, which of course you can also do, I mean, neuroscientists precisely do that, but you can also see neurons as just an on-off switch. Okay, and the power of the brain comes from not from the complexity of the individual neuron in this perspective, but rather millions and billions of such on-off switches connected together. And so I will spend a bit of time on discussing this very influential paper. And you'll see that, up till about 82, there are only a few, landmarks. So Alan Turing's famous paper on can machines be intelligent, or how do you test whether machines can be intelligent? So this is way before anyone thought that machines, you could actually make, the AI at the same level as what we have today. And then the first attempt at building machines which can look at data and make decisions. So the so-called perceptron. And then there was a big attack on this whole approach by Minsky and Pepelt in 1969, which effectively stopped all work on neural networks for more than a decade. And then two papers came out in the 80s. In 1982, Hopfield published his very famous paper in Proceedings of National Academy of Sciences, US, which essentially looked at the problem of memory from the perspective of neuronal network models. How do you make a machine associate memories with various kinds of stimuli? And in 1985, Hinton and his mentor Sitabrah came out with this idea of Boltzmann machine, and then on to restricted Boltzmann machine, deep learning, and so on, which I will not talk about, but let Ravindran talk all about it. All right. So the prehistory you can date to whatever you feel like, but in effect, the fascination of having machines which simulate life has been there for a long time. So if you see in the 18th century, there were like these clockmakers who made a sideline out of creating dolls which had elaborate machinery within them. So anyone who has seen Hugo will remember that there's this machine which kind of writes a letter. So it's essentially entirely made out of clockwork, right? So it's not a fiction. You actually have these machines in display in various museums in Europe, where you can actually have this doll write a letter. Similarly, you can have dolls which play musical instruments and so on. And then you also have a chess playing machine, which was built in 1770 and so on, right? So this idea that you can actually have machines which are almost lifelike had a big hold on the human imagination even back in the 18th century. But to think about how you can make thought itself algorithmic, that is how you can make machines think, like you are giving them a problem and they essentially come up with a solution independent of any humans actually engineering it. I mean, when you have this clockwork automata, there's some clockmaker who actually thinks a lot about, okay, how do you actually build these gears and levers and so on, so that it actually does what you want it to do. But how do you make machines which, without any human intervention, just given some stimuli, can come up with a solution? Like, you tell the machine, okay, cross the road. Then it has to figure out, okay, I have to watch my left, watch right, and then try to cross the road. But nevertheless, some idiot is going to come anyway, suddenly from nowhere. And so I have to keep looking everywhere. And so it has to pick up all of this just from experience without actually a human designer going and plugging all of this into its program. So how do you make machines learn? And this actually goes all the way back to early 19th century when George Boole came up with his famous Boolean logic. I mean, we, of course, nowadays associated with digital circuits, but Boole himself had in his mind coming up with the fundamental laws of those operations of the mind by which reasoning is performed. He wanted to automate reasoning such that machines can reason out of data given to them. So essentially, his idea was to come up with the nature and constitution of the human mind. It's a very, very ambitious project that he had. And essentially, it has a postscript. Claude Shannon in 1937 used this Boolean algebra to show that he could construct and resolve any logical numerical relationship, which is, of course, what led to design of digital computers. So you can actually relate, the design of digital computers way back to Boole. Then another stream has to do with the famous philosopher Bertrand Russell and his mentor Alfred North Whitehead, who in the first decade of the 20th century decided to come up with a solution of the problem that, given a few axioms, can you just by logical reasoning come up with all of mathematics? It's a very ambitious project. So they argued that if Euclid could come up with just a few axioms, and then all the theorems are just a result of applying those axioms and then logical reasoning on those axioms, then why not all of mathematics? Just come up with a finite set of axioms, and then effectively you can derive all kinds of theorems. Okay? And their magnum opus, Principia Mathematica, which was published in several volumes within 1910 and 1913, had to do with precisely that they have a certain set of axioms, And they just use logical operations like conjunction, disjunction, or negation, which in the language of Boolean logic are just and, or, and not combinations, and just ask, is this proposition true or false? So it's like an automated theorem prover, right? Now, of course, this venture received a big setback when Gödel showed you can have actually propositions which cannot be proved to be either true or false. And the other setback to this program was because of Alan Turing, who showed that there are propositions which are simply undecidable. So you can give me a theorem, but I will run it into my machine, a machine which is supposed to tell me whether this theorem is true or false, but the machine will never stop. It will just keep crunching numbers. And Turing didn't stop at that. He actually went on to become one of the founding fathers of digital computers. And then in 1950, he actually applied himself to ask the question, suppose a machine claims that it can think, or suppose you make a machine that claims it can think, and you claim that it can think. How do I test out whether that is a valid claim? Now, most philosophers here would now start getting bogged down into questions of what is thinking and so on. Turing didn't bother with those questions. Turing went straight to the point. He said that, look, if a machine discusses with me, and for all external purposes, I can't figure out whether it's thinking or not, or rather, let me put it this way. You don't actually get to see who you're arguing with. You just are, let's say, on a computer, and you are having a chat, or on a phone, you're having a chat with someone, right? And I ask, okay, you can ask any question you want, and you have to figure out whether the other person on this chat is a machine or a human being. And let's say after several minutes of this interrogation, you cannot figure out whether it's a machine or a human being. Then for all practical purposes, that machine has passed the test of intelligence. Right? If it can fool you successfully for however long you want, it has effectively proved itself to be intelligent. And so this is known as the Turing test. So in other words, Turing is giving an operational definition of intelligence. He's saying that intelligence is what intelligence does. And to some extent, you can argue that many of today's AI is already kind of crossing this Turing test. And then the next big landmark of our story has to do with these two people, the philosopher Warren McCulloch and his protege, the mathematician Walter Pitts. So Walter Pitts actually grew up in the streets, and he effectively found mathematics as a refuge when he used to hide in the library to protect himself from being beaten up by bullies. So he essentially taught himself mathematics, and he so impressed McCulloch as a teenager that at the age of something like in his early teens, McCulloch offered him a fellowship, right, in his university. And together they wrote in 1943 this famous paper, The Logical Calculus of Ideas Immanent in Nervous Activity. As Seymour Papert, one of the pioneers of AI, has said, that they were the first to recognize that the laws governing the embodiment of mind should be sought among the laws governing information rather than energy or matter. And so what they did was they said, instead of thinking of a neuron in all its glorious complexity, so this is the cell body, this is the axon, these are the dendrites, and so on, just replace it as a switch. So think of it like this, that there are inputs coming from various neurons. All of this information is weighted with certain weights, more about this later, which is then summed up and then compared against a threshold. If this weighted sum of signals coming from all the neurons exceed this threshold, the neuron is switched on, else it's switched off. Very simple, right? It's just a switch whose activity, whether it's on or off, depends on the activity of other neurons which are connected to it. And then using this, they essentially showed that you can build various logic gates like the AND gate, OR gate, and the NOT gate, and so on. And so therefore, you can build any arbitrary logical circuit that you can think of. And in principle, therefore, you can build arbitrary logic arguments, or you can make the machine answer any kind of complex logical questions by building the appropriate circuit. Okay, now what's going on? Why is it going to YouTube? Somehow it went into YouTube. Oh, okay, great. Thank you. All right, so and then so 1943 is when McCulloch and Pitts gave their proposition, but it was a just an idea. They showed that in principle you can build a machine to solve all kinds of problems, but there was a hitch. The hitch is this. Again, someone has to go and do all these wirings for solving a particular question. Okay. But ideally, you would not like to have someone go and do all the circuitry. You should have the machine itself figure out what circuitry it needs and then solve the question by teaching itself from past experience. That's what humans do most of the time, right? So you learn by experience. And the question was, how do you make a machine learn? And that question, for the first time, was attempted by Frank Rosenblatt, who actually died quite tragically young. But what he did was that he actually made a machine which took this McCulloch-Pitts idea of neurons as switches and connecting them together. But then he had another ace up his sleeve. He also had an idea about how to make these links reconfigure themselves based on experience. So essentially, the machine can learn. So learning added to McCulloch-Pitts kind of network gave you the first neural network, which Rosenblatt called the perceptron. Perceptron because his machine could, for example, be shown various images. For example, you can see there's an X marked in terms of lights. So, the red lights indicate X and the other lights are white. So there's a red X on a white background. And the machine would be able to see this because, it has a sensor array. And then it could recognize it as a particular state, which it calls X. And similarly, it can recognize a A, it can recognize a T, and so on. So the way it learned is that you show it various patterns and you tell it what that pattern corresponds to. So for example, if there are two slanted lines crossing each other, you say that this corresponds to a state called X. If there are two slanted lines joined by a sidebar, joined by a horizontal bar, you say that it corresponds to a state called A, and so on. And what it does is that it modifies the weights associated with the connections between these various switches until it manages to create something like a decision boundary where it says that all signals which roughly correspond to this idea of two slanted lines. So the X could be like this, or the X could be an italicized X, but they're all X's. So provided you have this basic form that there are two slanted lines which cross at some midpoint, then it corresponds to a state called X, and two slanted lines which are joined by another perpendicular line kind of corresponds to an A. So you could have these lines kind of oriented at various angles, but as long as roughly this looks like two slanted lines crossed by a perpendicular line, you will classify it as an A. So in some abstract space of all kinds of signal properties, you could divide between patterns which look like X and patterns which look like A. And this was happening entirely in an automated fashion. Now, this was fascinating, and not surprisingly, it actually led to a lot of expectation. There was media speculation that thinking machines were just around the corner. In the 1960s, we would finally see intelligent machines and so on. Let me not go into the details. This is basically just to show how, if you are interested in a bit of maths, that you can actually think of this as some kind of a function of the weighted sum of the stimuli. And just by changing the weights in a particular fashion, you can make the decision boundary between the signals you're receiving such that you could make it go through exactly on this space such that it divides all the signals which correspond to, let's say, X with all the signals which correspond to X. Okay. So the next important paper, I would say, has to do with these two people, Minsky and Peppert, who actually showed that if you want a machine to, let's say, divide or distinguish between signals where where one class of signals actually falls in this space, a middle space, and the other class of signals falls in this part on the left-hand side and also on the top right hand, then it's impossible to use the perceptron of Peppert, perceptron of Rosenblatt to do it. And that's because, notice what this does. In the single-layer perceptron, what you're doing is you're using a single line. We're using a single line to divide the space of signals, whereas here what you need are two lines. Okay? So using a simple perceptron where you have an input layer where the stimuli is coming and an output layer which you read off as the decision, whether it's an A or an X, it's impossible to create this kind of a classifier. And this is actually nothing but the exclusive OR logic gate, where exclusive OR logic gate says that you switch on if signal 1 is on and signal 2 is off, or signal 1 is off and signal 2 is on. But if both are on or both are off, then you switch off. So this is the exclusive OR. One of the signals must be on and the other signal must be off for you to switch on. And so you can't do XOR logic with a simple perceptron. And this effectively stopped research in neural networks for more than a decade. But of course, note that there was a vested interest behind Minsky and Peppert showing this, because they were the pioneers of the program-based AI, which said, forget about neural networks, we're just going to write smarter and smarter programs, which is going to simulate human-like responses. About 1949, another thing happened. Remember, 1942 is when this great paper of McCulloch and Pitts came out. In 1949, the Canadian neurophysiologist, quite unknown to McCulloch and Pitts, and he himself didn't know about the work of McCulloch and Pitts, came up with this idea of how actually we form memories. And he had a very simple idea. He said, neurons that fire together, wire together. In other words, if a particular neuron 1 is firing, and at the same time neuron 2 is firing, then over time, the connection strength between neuron 1 and neuron 2 is gradually going to get stronger. On the other hand, if neuron 1 fires and neuron 2 doesn't fire, this is going to cause the connection between 1 and 2 to weaken. So if this looks like, not very understandable, just think of this. It's like, building friendships. Two people, if they smile at the, same jokes, or, they smile when each is, happy, and they cry when, the other is sad, their friendship is going to go stronger. But, if one laughs when the other is extremely sad, chances are that gradually the friendship is going to go down. So think of friendship as basically the connection strength. Okay? So if both are coactive, friendship is going to get stronger. And if they are differentially active, the friendship is going to go down. So that's effectively the Hebb rule. Okay. And you might ask, okay, is this really biological? Well, this is one of those very interesting ideas which was, announced without any biological evidence to back it up, but it turned out to be true. So in 1966, for the first time, people saw that indeed there was something like the Hebb rule going on in the brain, which was called long-term potentiation. Effectively, what is happening is that over time, as neuron fires, if the other neuron, which is connected to it, also fires, gradually the synaptic strength between them gets stronger and stronger. Okay, so there is a biological basis we now know for this Hebb rule. And this makes it possible to now finally understand how human memories work, which remember are very, very different from computer memory. So how does computer memory work? So they use something like random access memory, where you need to know the address where you have stored a particular data. Okay? So for every piece of information you wish to store, you have a particular address of where in the random access memory this bit is stored. If you lose this table, if you lose this map from information to address, the information may be there, but you have no way to locate it. By contrast, we remember information in a very, very different way. So, I can't remember your name, but I will try to recall it by remembering, well, your name reminds me of a flower which is kind of red, has a nice smell. I'm sure, many of you have seen this famous ad which used to run, a few years back, where one person in a party is telling the other, I went to this wonderful restaurant the other day, and the other person says, oh yeah, what? So this person says, there's this flower, right? Very nice smells. He said, lotus? No, it has this red color. Rose? Ah, yes, rose. Rose, darling, what's the name of the restaurant we went to last night? So, we have this way, right, of remembering partial information, and from there trying to get to the whole information, right? So how do we do this? And this is very famously, written in literature by Marcel Proust. So in Proust's Remembrance of Things Past, he talks about, how he came home tired. He had a madeleine, a cake, and the moment he bit it, it took him back in the past to a memory of the first time he had that madeleine cake when he was a child in the room of his aunt. So we do this all the time, right? Without even conscious thinking. We smell something, we smell a loaf, freshly baked loaf, and it immediately takes us back to our childhood when maybe we used to have a bakery in our neighborhood and you used to walk past it. So it immediately reminds you of that incident. So how does, so the fact that human memory is associative is of course known to everyone, including, famous writers like Marcel Proust. But how do you have associative memory? And so Hoffield's great idea, which came out in 1982, was to show that, look, the simplest way to show how the associative memory works is to think of it as some kind of an attractor network. So what is an attractor network? So his idea was that, look, the memories that we store are kind of like the valleys of a landscape, and your mental state essentially corresponds to a ball which is rolling around this mental landscape. Whenever you let it go, it will roll down to the nearest valley bottom, and that's when you recall a memory. Okay, so I have with me. Okay, I'm not doing product placement, believe me. So I won't show you the name of the box, but effectively, Hoffield's idea is our memory kind of corresponds to a landscape like this. So what do these corrugations correspond to? It's energy. Okay, where this energy comes from, we'll come to in a second. So now this marble ball over here essentially corresponds to our mental state. Right? And so what is happening is, initially, let's say we are somewhere, and then there are noise, there is fluctuation. Where is this fluctuation coming from? Because we are all the time subject to various kinds of sensory stimuli. So this is causing this ball to jiggle all around. And so it's going from one valley to another valley and so on, right? And sometimes it goes all the way out, and you basically are going nuts, or maybe you have reached some state of moksha. Thank you. All right, so what Hopfield did was he showed that you can take this basic idea of switches, and you could essentially make the connection weights be evaluated by the Hebb rule. Now, one of the things he did was that he assumed that whenever neuron I is connected to neuron J with some weight, neuron J is also connected to I and with the same weight. Now, any biologist worth her salt will tell you this is nonsense. Neuron A connecting to neuron B does not imply neuron B is connected to neuron A. Moreover, neuron A could be excitatory and neuron B could be inhibitory. So neuron A could be, for example, giving a plus weight to neuron B, and B could be giving a minus weight to neuron A. So this is clearly this assumption of symmetry that the weight from I to J is always same as weight from J to I is obviously wrong. But this allowed Hopfield to write down an energy function and show that this is nothing but a random magnet. And so Daniel Amit, a famous physicist who actually has worked on this Hopfield model for a long time, called it a brilliant step backwards. By moving away from biological realism, Hopfield actually allowed a lot of the machinery of statistical physics to be immediately brought to play to solve various questions about neural networks that had stumped neuroscientists and computer scientists for a long time. And so what Hopfield was doing was that he was using this idea of Hebb, that whenever neuron I is active, neuron J is active, in this particular kind of rule where he's just associating whenever neuron I is active, neuron J is active, and just using this idea to calculate the connection weights. And this allows him to store various kinds of patterns that you can see over here. So for example, if you want to store this picture of a dog, you use that rule of Hebb to calculate all the weights, and then you show this kind of a noisy picture. Okay, you know that there's something like outline of a dog, but you can't really make out. Now, but using these weights, now you can actually converge to the original picture of the dog. So it's like starting with a very partial information about the memory and then converging to the full memory. And Hopfield showed that you can actually think of it in terms of an energy landscape, similar to what I just showed you, that you can store these two patterns, and starting from anywhere, because you have evaluated the connection weights according to the Hebb rule, you're now going to converge to the stored pattern. So for a single pattern, this is nothing but actually the ferromagnet, where what does a ferromagnet do? So a ferromagnet, if you have, if you think of it as a system of spins, and so for example, if you go by the famous model of Ising, or which is also often called the Lenz and Ising, Lenz was the advisor of Ising. So you can think of a magnet as lots of tiny spins, which could be either pointed up or pointed down. And if there's no connection between any of the spins, essentially they'll be randomly aligned, right? So roughly half of them will be up, half of them will be down. So in the absence of interaction, there'll be no order. But now if you put in interactions, which says that in a ferromagnet, every spin tries to make its neighboring spins to be aligned with them. So if you're up, you want to make your neighbors up. If you're down, you want to make your neighbors down. So in that case, essentially what you'll have is perfect order. Everything goes up, even if you start with randomly aligned spins. So you have spontaneous occurrence of order. But the problem is this is only true for no noise or no fluctuations. The moment you have fluctuations, this order is lost. Now, Ising thought that, well, this is true for any dimension. And so therefore, spontaneous order is not possible except at zero temperature. So it was left to the famous physicist Lars Sonseger, also a Nobel laureate, to show that this is not true if you go to higher dimensions. So for example, if you look at 2 dimensions and you have interactions with not just your left and right, but also your up and down neighbors, then essentially, provided your thermal fluctuations is not too high, over time, your spins are going to get aligned so that you'll get perfect order, assuming the thermal fluctuation is low. And so this tells us that by varying the noise or thermal fluctuation and varying the field, you can get a transition from order to disorder, or seen the other way, you get disorder to order. And how this order to disorder happens can also have 2 kinds of ways. So you can have either a field induce a transition. So this could be what is known as a first order phase transition. So here, you see a railway station where passengers are moving, each in their own location. Suddenly there's an announcement. Train number 120434 Kanyakumari is coming through platform number 7. And then suddenly you see a very ordered stream of people going along this. Suddenly from random movements, you have a completely ordered transition. All right. But you could also have a cooperative phenomena or a continuous transition where you have people moving around on the street. And we used to do this in Calcutta. The three of us would get together and very, attentively look at a window on the second floor of some adjacent building. Nothing's happening. Okay, we're just staring there, but very soon people would come along and say, "You each other," and then very soon there'd be a crowd, and of course the three of us would make our escape. Okay, so nothing's going on. There is no field. It's just completely spontaneous ordering, where everybody's looking at what's going on in this window. Okay, so what Hopfield did was he took this idea of spin models from physics as a model for complex system, and he showed that for a single pattern, this is exactly like a magnet. But for multiple patterns, you have the problem that, okay, you have some field which is, inducing it to go towards the desired pattern, but you also have a crosstalk. So what is this crosstalk? The crosstalk essentially comes from that for one pattern, the system wants to go, make you go to the nearest valley. But if you have many patterns, then you have like this, right? You have lots and lots of valleys, and they have conflicting constraints. So it's like, the classic love triangle, the favorite staple of Indian cinema. So you have, two characters who are basically attracted to the same person. Now, if all three of them are friends, then it's a very happy, triumvirate. But if you have a situation where, this person likes both of them, but they, of course, hate the guts of each other, then you have problem, you have tension, right? And that's effectively what happens in magnetic systems also. So if you have, multiple patterns stored, you can have situations like this, where there's a positive weight connecting this spin and this spin, but there are negative weights which are connecting this pair of spins, this pair of spins, and this pair of spins. So you can see that you can align a spin in, let's say, down direction. And because this is negative, this should ideally be in the up direction. And then because this is negative, this should also be in down direction. But now you have a problem. See, this one, if it's down, it will violate this condition. But if it's up, it will violate this condition. So you have a problem. Right? This leads to tension. And the moment this happens, your energy landscape, instead of being a smooth valley like this, becomes this very rugged landscape, which leads to gradually the erosion of the memory states. And so essentially Hopfield showed that associative memory or memory recall in associative memory is nothing but this very complex energy landscape where you are trying to get down to the nearest valley bottom. And so you can add noise to this to show that there is some limit of how many patterns you can store in the Hopfield model. And surprise, 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 although he had taken a step back from biology to do this, in 2003, people did experiments with the mouse visual cortex and found precisely these kinds of attractor networks, where a whole group of neurons essentially either all go are firing like mad or become extremely quiet. So basically, they have this on or off kind of states, exactly similar to what Hopfield was predicting. So sometimes, by taking a step back from biology, you can actually make a lot of advance. Now, problem, of course, is that Hopfield's assumption was that everybody's connected to everybody. But we know that the brain has a hierarchical arrangement. So we know that, this is a classic picture that you see in a life science book, right? The eye sees something, then your sensory neurons are activated, then they activate interneurons, and then finally your motor neurons are activated, which leads to action. Let's say going and patting the cat, but if you're a mouse, you better run, right? So it can basically guide your action. And this is where Sejnowski and Hinton came up with. So they said that, hold on, why not have a Hopfield model? But unlike the Hopfield model, where every neuron is like subject to some stimulation, now assume there are some hidden nodes exactly like in the perceptron. Oh, sorry, I didn't talk about it, but like the perceptron didn't have any hidden nodes, but we know that you can solve the XOR problem if you now actually put in another layer, intermediate between them. And so the idea was like, if you have hidden nodes, so there are all kinds of connections here, which I didn't get time to draw, you can now show that you can have higher order correlations, which are not just trivially connected to the average of the states or just pairwise correlations. So this is actually nothing but exactly the XOR problem. So just as to solve the XOR gate, you need to put at least one more layer between the input and the output. So Sitabrah and Hinton showed that if you now have hidden nodes in the Hopfield model, you can actually solve very complex problems. So let me stop at this point by just pointing out that actually there's a lot of evidence for finding for hierarchy in the brain. And so this is work done by a former PhD, brilliant PhD student of mine, Anand, and postdoc Shakti, which shows that actually brains have a lot of these hierarchical characters. And this is very robust. You can look at it across human subjects all the way from, across different ages and so on. Moreover, they also have community-like characters. So you have networks which are arranged in hierarchical layers, but which are also arranged in compartments. And so the question is, why modular hierarchies? So this essentially is saying that, look, you need to use parallel processing. So there should be multiple streams by which information from, let's say, visual pathways, auditory pathways, olfactory pathways are processing, but you also need to process them. You need to transform them from initial layer to intermediate layers to final layers. And so that's why this is looking like the structural organization that the brain is using. Okay, so I'm sorry I took on so much time. Let me end at this point, but this is just the beginning for Ravindran's talk. Thank you.
Okay, I don't want to spend too much time. But if you still becomes here, I want to introduce Professor Ravindran. He heads the Department of Data Science and Artificial Intelligence and the Boltzmann School of Data Science and Artificial Intelligence. And Robert was Center for Data Science and Artificial Intelligence, IIT Madras. Along with that is also the monthly faculty fellow at IIT Madras. Currently, his research interests are centered on learning interactions, spanning the areas of geometric reinforcement. So, okay, in the sense. So, we will have question answer after both the talks are over. Okay, I'm sure a lot of you have several questions to ask. We'll go on as much as possible. And I hope Sitabrah and Ravindran will be happy to answer all the questions. Sitabrah, come. I have
I'm just making sure that I'm no longer telecasting.
Just move that window to this.
Sorry?
You are mirroring, right?
Huh? I am mirroring.
Yeah.
Just she's European.
Okay.
Are you ready, sir?
Yes, sir.
Okay.
Just one sound check on Zoom.
Okay.
I'm fine. Okay, great. So Sitabrah is a tough fact to follow. Oh, that's even tougher for me to follow. Oh, he just sat cross-legged on the floor. Sure. Okay. Sure. So I'm going to, my talk is titled Going Deeper because everybody talks about deep learning and things like this. I'm not going to go any more deeper than what Sitabrah was doing in terms of math and so on and so forth. And in fact, a lot of my slides are just pictures. Okay. So all of you have been trying to follow all the
the equations on Sitabrah slides, take a breather. You'll have a lot of pictures. And so one other thing is, I actually don't have slides on RBMs. I thought you were going to do RBMs. So what I will do is, when we come to restricted Boltzmann machine, I'll talk to you about what they are, right? Maybe not on the slide. I'll just introduce you to very briefly. Okay. Let's get going. So this is a slide I made, right? So this is my history of AI, because I wanted to point out that whenever people talk about AI, immediately after that, hype starts. As soon as we have some amount of small amounts of success in AI, immediately hype starts. Right? This because as humans, we are so fascinated with this notion. Like Sitabrah had this, the simulacra experiments and other things going back way like centuries, right? Not just decades, right? Where people are trying to have artificial beings that could exhibit some kind of intelligence. So we have this innate, I don't know, maybe a drive to look for other species that are as intelligent as us. I don't know why it's the case, but we are very quick to latch on to any early signs of intelligence and then try to post it up, right? And so I'll come back to some of these things. And I believe where we are now is one of the peaks of the hype cycles as well. So the two Nobels, not just physics, right? So we got chemistry also for AI this year, right? So it's things are going crazy, right? So let's get going. Let's step back, right? I mean, some of this is actually valid. So these are all stories and screenshots from different AI products and so on and so forth. And so one thing I like is this series of news stories I put together. So that is math, AI helping to solve math. That's chemistry. Right, that's physics, and that's biology, and that's aerospace. Right? Okay. So AI is kind of impacting almost every field of science as well, right? So maybe it's okay for us to have some amount of elevated expectations now, right? And so we already saw the perceptron. This is the on-off switch that we talked about. This is back in 1958 is when Rosenblatt came up with his algorithm for finding these connection weights and so on and so forth. And as soon as that came out, right? And this is the hype that Sitabrah was talking about. This is a newspaper story from back in 1958. You can look at it. The Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Okay, so that is the level of expectations people had on this, right? So literally, what it was implementing, right, is like the step function. So that's basically what the perceptron was implementing. It was doing this kind of a step function, and so you can ask, okay, yeah, sure. What are you going to do with this? And so people actually used it to solve various kinds of binary classification problems, and even today, a lot of AI is still solving binary classification problems. It's just that the problems that they are solving is getting more and more complicated. So you could do things like, hey, I can look at all these features and tell whether a movie review is positive or negative, right? So if I sum up everything, you already saw I didn't walk through I actually removed the equation from this slide. But so you already saw that from Sitabrah, right? So it will basically, I'll take all the features, I'll take a weighted sum of the features. If it's above a certain threshold, I'll say you like the movie. If it's below the certain threshold, I'll say you didn't like the movie. Likewise, here is something on whether the writer is a male or a female, right? So now the input for both these perceptrons is the movie review, right? Depending on what you want to predict, right? So your problems will change, the models you learn will change, the weight will change, etc., right? But now, when you start getting into more complex situations, right? So here is an example where I want the output to be positive in like this kind of a range. This is the XR problem. I didn't, so we already saw the XR problem. So how do you get this kind of a range, right? So we know that the perceptron can implement steps, right? So how do we get it to implement ridges? Right? So one way to do that is to actually add another layer. I think this is Sitabrah very quickly alluded to this towards the end of his talk, where we talk about what are called hidden neurons. So why are we calling this as hidden neurons? Because you cannot see the output of the neuron, and nor does the neuron get the input directly from the outside. So this basically has no connection to the outside world. So therefore, it takes the input from the first layer. So this is the input. So it gets transformed. So it sees some kind of a transformed input. And the output of this neuron is not visible directly. It goes into another neuron, which then finally gives you the ridge. Okay. So now if you want to do something more complicated, I don't want a ridge. I want you to give me a +1 in this peak alone, right? The rest of it should be 0. Then what do? Basically add more neurons. Right? So you can keep adding more layers, more neurons to start implementing more and more complicated functions, right? And okay, so before I don't want to head off into the actual learning rule that Rosenblatt came up with, because it's not quite relevant to our further discussions. But another way of computing this solution is to look at finding the the gradient, right? Looking at how the error in my prediction. So I'm supposed to say there's +1 now. I'm saying it's -1, right? That's some kind of an error. So how does the error in my prediction change as a function of these weights in the perceptron? Right. So if I can look at that, then I can go in the direction which will decrease the error. I can change the weights in the direction that will decrease the error. If I increase the weight, if the error will go down, I'll increase the weight. Right? So that's basically what I end up doing, right? So this is essentially what we're talking about. This is a curve that maps the error, right? And the kind of the x-axis here is some representation of the parameters that you're tuning, right? These weights that you're tuning, and as you keep moving to different parameter settings, you can see that the error is going down. And ideally, what you would like to do is follow this gradient, right? So you would like the error to move here if your parameter is somewhere here, or if your parameter is somewhere here, you would like it to come down so that you come to the minimum of the error. And you can see what happens to the function as the error changes, right? So that's basically what you're trying to do, right? So this is one very popular way, and I'm sticking with this as the way to estimate all the things. I'm not talking about Hebbian, I'm not talking about the perceptron learning rule, because this is literally what all this modern greatest, your ChatGPT, everything does, okay? So, but then the simple gradient rule is fine as long as I have one neuron, right? When I start having multiple layers of neurons, I run into problems. But even with one neuron, I run into a problem, right? So what is the problem? Okay. I mean, I see some of my students in the audience. I don't want to ask them questions, but it's okay. So one of the problems is that I have a step function, right? The perceptron actually has a step, right? So that step function, if people remember your high school math, you can't take the derivative of that step function. So you cannot find the gradient whenever there's a step function. So the first thing people do is replace the step function with something that's called a soft response. These are all things that evolved over time, right? So in fact, this happened somewhere in the late 70s to early 80s when people started talking about replacing the step function with this kind of a soft threshold, so they can start thinking about gradient of values. So that's the first thing that people did. The second thing they had to come up with, I'm not getting into the technical details of it, is to figure out a way. Let me go back one slide. Let's say that this is the output, right? I can find out how the output's error will change with respect to these weights, right? These parameters are GC because they're directly connected, right? What about these guys, right? These connections, they don't directly connect to the output here, right? So how will I find the gradient of the output with respect to these connections? Now we all know the answer, right? In fact, it's even taught, in very, very early calculus, you know about chain rules of differentiation and things like that. Everybody knows this, right? But then back in the 70s, right? So people are actually stymied. They didn't really know how to go ahead and do this thing. And so there was a lot of work that went in. Finally, people figured out a way in which they could use this chain rule of differentiation. And just like you go forward from the input to the output, they could go backward from the output to the input and find all the gradients. By gradients, I mean the direction in which the error is changing. Right? So they could do that very easily. And so once you had this kind of a back propagation mechanism, then you could basically take whatever complex error surface you had, right, and then follow the gradient to get to the minimum of the error surface. So that's basically the idea behind back propagation, right? And so back propagation actually we really can't attribute it to one person. If you actually go to Wikipedia page about backpropagation, there's a one whole page, like if you look, one whole screen of citations to the backpropagation algorithm. Like not just, there is no one person who has invented it, right? It has been invented repeatedly several times in the 70s and 80s. In fact, there are some instances that goes back even earlier where people have come up with some version of this backpropagation algorithm, right? But what happened was the most popular variant, for whatever reason, the one that Rumelhart, Hinton, and Williams published in 86, right, somehow became very popular and kind of triggered the revival of interest in this kind of connected neural learning, right? So this is called the connectionist approach, as opposed to the programmatic or symbolic approach, which Minsky and Papert were, and others. Quite a bit of people were popularizing back then, right? So this kind of kickstarted the interest in this kind of connectionist approaches, right? And so a lot of work started happening. Right? But then what happened was, backpropagation was great, right? But by late 90s, right? So people, not even late 90s, like mid 90s, right? It didn't even last a whole decade, right? By mid 90s, people started getting a bit disillusioned with how backpropagation was not able to solve really hard problems. It is great at doing a whole bunch of different things. In fact, when I was in grad school at that time in the mid 90s, and so I was reading as many papers about neural networks and backpropagation from non-computer science, non-AI, non-mathematics sources, right? In fact, I remember reading papers from petroleum engineering journals and so on and so forth. So everybody had gone crazy and they were using neural networks back then, right? But what was happening was in the AI community itself, the people are kind of hitting this kind of plateau as to what they could do with it, right? The first thing is, it was not able to make good use of networks that had more than 2 layers. It could, I mean, you could go up to 5 or 6 layers, but only, it was a nightmare to get it to work numerically. Right, so there are a lot of issues in getting these things to be very stable in computation, so on and so forth. And the second thing is, we already talked about this kind of recurrent networks, right? The Hopfield network, and then we also had the Boltzmann machine, where there are connections between the hidden layer and the output layer, and then reciprocal connections, right? So for these kinds of models, we couldn't train them using backprop. It was really, because the way backprop numerically handles that is basically to set up almost an infinite backpropagation, right? And that will not, that did not numerically work out, right? So there are a lot of problems with this. So people kind of forgot all about this, and they needed to come up with, other learning models, right? So there was this whole direction of research on kernel approaches, kernel methods, which I'm not going to get into, which became popular in the late 90s, right? And but then I was telling you that backpropagation didn't work well because we couldn't use networks with multiple layers, right? So why should we go deep? In fact, that's a question a lot of people were seriously asking, because there was this universal approximation theorem that was proven back in the early 90s, which basically said a single hidden layer neural network, right, can approximate any continuous function arbitrarily well, given enough hidden units. So that basically means that you don't have to go deeper than 2 layers. Right? So you can just have 2 layers of networks and then solve any problem. Right? That's what basically says. But the challenge here is, this is a representational theorem. It tells you that such a network exists, right? But it doesn't tell you how to find it, right? Whether you can find it or not. So that's going to be a challenge, right? So so the reason to go for deeper architectures is that they can be representationally efficient. Right? What do I mean by that? So you can have fewer computational units for implementing the same function. So here is an example. So Boolean functions, which we already encountered in Sitabrah's talk, that that you can express with like the order of d times log d, right? So where d is the number of Boolean variables that you are having, right? So you can express that with d times log d by having a deep computation architecture. If I want to describe it with using only 2 layers, right, I'm going to need 2 power d. Way more computation, way more units that I would need than I would need by going deep. Okay. So what are the advantages of this? So when I'm trying to find these parameters, right, automatically, right, then I require a lot less computation because I have so much fewer parameters than what was originally there. I require a lot less computation. And the second advantage I'm going to get is that a lot of this, this gradient-based computations require you to give data, right? They need a lot of data points, a lot of inputs on which they are being trained, right? So if I'm going to give you a review and I want you to know who wrote it, right, whether a male or female wrote it, I have to give you millions of examples for you to train more and more parameters, right? So by reducing the number of parameters, I'll also reduce the data requirement, which makes it all the more tractable. So that's the first part of it, right? And the second advantage of going deep, right? Because again, we already know that our brain is hierarchically organized, like as Sitabrah mentioned, right? And so the deep representation allows us to have this kind of a hierarchy of representation. So what do I mean by that? So the input is going to come in terms of pixels, like we're looking at an image, right? It's going to come in terms of pixels. Then the first layer, right, will kind of respond to edges. Like very simple things, like okay, this side is light and that side is bright. Okay, then this one neuron will come on, so on and so forth. Right? So you have a bunch of neurons that's going to respond to these edges. And the next layer will potentially respond to object parts. Right? So you can see now, you can see that there's an eye and a mouth and a nose and all these things. And each square is a feature for which a neuron is being tuned. Finally, the third layer is going to start representing, responding to objects. Right now, you can almost see full faces and so on and so forth. And then if you have more layers, then they can look at more complicated features that you're going to learn. So this kind of a hierarchy of representations can be learned when you start using deeper models. And that is one of the reasons the models become more compact. Okay, there are more technical reasons for this, right? I'm not going to get into that. But also the final thing, the proof of the pudding is in the eating. So it turns out that all of these deep architectures are so much better, right, than a lot of things that people have tried to do with shallow architectures, right? But having said that, I have to mention that there is a recent line of research that's being pursued by a team out of UT Austin that actually showing that with the increased computational power that you have, with all these GPUs and everything that you have now, you can go back to doing shallow and wide networks and still get comparable performance. So it's still not a settled question as to what is the right direction to go, but a lot of work that happens, right? So now, great. So now we have kind of argued that deep networks are good to have, and we also said, plain vanilla backprop doesn't help in training deep networks, right? It kind of numerically it becomes very unstable. So how do you train deep networks? So this is where you get into the second contribution of Hinton, which was actually mentioned in the citation for the Nobel Prize. So even though he kind of popularized backprop, that's not what he got the Nobel for, right? So that's the thing. So if you ask what is Hinton's contribution, 80% of people who have a superficial familiarity with the history of AI would say backprop. Right, but that's not what he got his Nobel for. It was a Boltzmann machine, and then how he used a specific restricted form of the Boltzmann machine to train deep networks. So he kind of showed people how to train these very, very deep networks one layer at a time. So the problem was when you're trying to do back propagation, remember I was telling you, you go forward for computing the output, and then you start from the output and you start going back when you're computing the error, the gradient, right? So what happens is that if you go back a few layers from the end, right? Now the influence of each individual feature on the output, right, is going to be modulated by thousands of connections. Okay. I didn't want to block the screen if I'm standing there, so I didn't realize that it had a camera running on it. Anyway, where was I? So it's actually going to go through like thousands and millions of parameters before affecting the output. Right. So if you take a single weight and say the seventh layer from the output, right, it's going to go through 7 layers of weights before it actually impacts what will be the error. So computing the gradient using the traditional back propagation way, right, kind of tells you that the gradient is almost 0. right? And you're not able to actually find the right answer. Okay, so that's the problem, right? So what Hinton said is, no, let's not do it that way. Okay, let's actually train these layers one layer at a time instead of going all the way to the output and then propagating back. So what is the problem doing it one layer at a time? We don't know what the output of this layer should be, right? We know what the output of the last layer should be. It should tell me whether it is male or female. But what about all the layers in between? What should their output look like? So we don't know. So he came up with all these mechanisms where you could do kind of unsupervised, training of this individual layers. And so both of these approaches, so he proposed one for training deep belief networks, another one for training what are called deep autoencoders. I'll explain these in the next couple of slides. And both of these used a form of the Boltzmann machine called the restricted Boltzmann machine. Okay. So what does the restricted Boltzmann machine do? So remember, the Boltzmann machine basically introduced the concept of hidden neurons, right? So you have neurons that are visible, whose output you can read out, and you have hidden neurons whose output you cannot read. Right? So there is this connection between the hidden neurons and the output neurons, right? So the original form of the Boltzmann machine that they proposed, any neuron could be connected to any other neuron. So the visible neurons could be connected to the visible neurons. They could also be connected to the hidden neurons. And likewise, the hidden neurons can be connected among themselves. They could also be connected to the visible neurons. But the challenge when that happened was that the finding out what the right weight should be became intractable for very large number of connections. So what the restricted Boltzmann machine does is two things. One, it says that connections can go only between hidden neurons and visible neurons and vice versa. Within each layer, there can be no connections. Okay. So what this does, it simplifies the form of the energy function tremendously. So the energy function that you are using, that actually this neuron, this restricted Boltzmann machine represents, gets simplified extremely. And there are many approaches for training this efficiently. And Hinton proposed a specific algorithm called contrastive divergence approach. Right? The contrastive divergence algorithm which Hinton proposed was, till today people use contrastive divergence. Right? It's not like it has not been superseded by anything else, but it actually basically told you that, hey, the way to train these models to kind of represent a memory, right? That's basically what we are trying to do, right? So we want to remember an input. The way to do this is to say, give it an input that you want to remember, and give it an input that you don't want to. Right, and you try to make sure that you maximize the difference between the two. That's what the contrastive divergence idea is. So basically, he came up with this contrastive divergence algorithm for training this restricted Boltzmann machine. So that worked very efficiently. And now what he does with these, right? So I'll give you this. So basically, what he is, the first algorithm he proposed was the deep belief networks, right? So the idea behind the deep belief networks is essentially to mimic the hierarchical nature in the brain. So you start off with the layer at the bottom, which is the input. Right? This is the one that you are seeing, right? The image you are seeing or the memory that you want, that's the input here. And you go all the way down to multiple layers. And each layer is potential, all of these are hidden. None of these are visible, right? The only visible input is the only visible layer is at the bottom. The one where you are actually going to read out your output, right? This is the only visible layer, and everything else above this is hidden, right? And you have this hierarchy of hidden layers, so that progressively they learn more and more complex features to help you store the pattern that you want to remember. So that's basically what this is, right? So what the way the deep belief network is organized is as follows, right? So you have all these layers of hidden neurons, and the final two layers of this deep belief network is organized as an associative memory, represented by a restricted Boltzmann machine, right? So from here, the connections go like this, right? And at this point, you have a Boltzmann machine, right? The restricted Boltzmann machine. And now what they did for training this was the following. You start with the output layer, then add just one layer to that. Just this one layer. Treat this as a restricted Boltzmann machine. Now you know how to train this restricted Boltzmann machine. You train that. Now what you do, so these activations that are coming from here, right? So this So from the input to H naught, you will have some input going. From H naught, you will have something going to the output. Right? Now, instead of making that go to the output, you make that go to H1. Now you have H naught and H1. You train that as a restricted Boltzmann machine. So after you train that, you take the output of H2, make it go to H3, and then train H2, H3 as a or H1. Yeah, you see what I mean, right? So first you train the input and H naught, and then H naught and H1, and then H1 and H2, H2 and H3, all the way till the top. Right? And once you have done this, you have basically trained the entire deep belief network. Okay? So that's basically the layer-wise training, and he showed that you could go arbitrarily deep, several tens of layers deep with this way of a layer-wise training of these. So that's what I'm saying, right? So whenever you want to generate the image, you start from here and do your computation all the way to the output, and it will retrieve a memory for you, just like you would do in the Hopfield network or in the Boltzmann machine. And when you're training the parameters and estimating the parameters, you go from the input all the way to the output. So that's the idea behind deep belief networks and how you train this. And then there's other model that has actually got a lot more traction than deep belief networks. In fact, Hinton has a series of papers on using deep belief networks for solving a lot of various problems. I mean, the problems with computer vision, problems in remembering patterns in image patterns, sound patterns, text patterns. He has done this across all kinds of input modalities that humans use for interaction. He has done that on deep belief networks. But unfortunately, the community at large did not quite latch on to the deep belief network part, even though he managed to show that you can get very good performance. They've actually went more into this kind of a model, which is called as an autoencoder. So the idea behind autoencoders is that you have an input layer of neurons and you have an output layer of neurons, right? And the goal is to reproduce the input at the output. Somewhat similar to what you are doing with the Boltzmann machine and Hopfield network. It's just that there it was more like a recurrent connection. So you have the input, and then the same neurons act as the output also, right? Here you have a separate layer called the output layer, and then you have the input layer. And then the hidden layer, right? The latent layers that you have here, the hidden layers implement certain kinds of constraints. It could be that you want the hidden layer to be of a lower dimension than the actual input itself, in which case you have to learn how to compress that, learn a representation, and then reproduce it. Or the hidden layers have to implement some kind of other constraints like orthogonality, etc., etc. Right? Of course, you can set this up to be a deep autoencoder. Right? You can start off with say 1,000-layer input. You can then go to 500, and then you can go to 200, 110, and then go back all the way to the output. You could do it that way. It turns out that backpropagation cannot train that effectively at that point. Right? So what they did was they basically set up a simple autoencoder, trained this. This you could train using backprop because it's just a 2-layer network, right? You're able to train this using backpropagation, and then you remove this part. Right? Then you train this as an autoencoder. Keep going. And now, whatever you have learned here, right? This is the smaller feature. So you start off, let's say you start off with a 1,000 dimensional input. You reduce it to 500, then reduce it to 200, reduce it to 100, and then the 100-dimensional vector directly gives you what the output should be. Okay, so you could do it this way, and so this, what you did now, is called greedy layer-wise pre-training, right? Even in the deep belief network case also, when you are doing the pairwise thing, it is called greedy layer-wise pre-training. Why is it called greedy layer-wise pre-training? Because once you have trained one layer of weights, you never go back and change it. So whatever you think is the best when you are training this autoencoder, you keep it that way. You never change this weight. After that, you only change the weights that are coming further downstream. Therefore, it's called greedy because you never do any backtracking to change it. So it's greedy, and layer-wise, it's called pre-training because you're not really looking at male-female classification problem while you are training these, right? You're basically training it to reproduce the input. You're basically learning just the input distribution. That's basically what the idea is, right? And so what? So this particular structure that I told you, These architectures were proposed later, right? It was actually started this other paper by Benjio and others in 2007, where they said, hey, instead of doing RBMs, we can do gradient-based training also, and we are getting good results. The original 2006 paper, which Hinton and Ruslan wrote, they actually talked about using RBMs. So each one of these, autoencoder layers that we are talking about were trained as RBMs. Right? So here is the first one. So the input has a 2000 dimension. So basically, they connected it to a 1000-dimensional hidden layer, and then trained this as an RBM. And then they connect the 1000-dimension to a 500-dimension thing, and then trained this RBM. So like this, they did this every RBM. And now what they did is they kind of they call this as they call this as unrolling. So what does unrolling do? It takes this RBM, right? You have these weights that you've learned here. They make a copy of these weights, right? And basically, when you go from, this is from 2000 to 1000 is W2. So from 1000 to 2000 also, they put the same W2. Okay, they kind of flip the weights and then put it on the other side also, on the output side also. 5 minutes, okay. Oh. Then that's basically what the final thing. So basically, what was the impact of doing this layer-wise training? Right. So Hinton and others showed that you were getting state-of-the-art performance in image processing, computer vision, text, etc., etc. But then the question is layer-wise pre-training the only way to do it? There are a lot of problems with layer-wise pre-training. It's kind of slow, and you have to kind of do it in a sequential manner, and so on and so forth. And so at this point, people had a lot of experience with backprop. They kind of figured out why backprop did not work. I mean, the real reason why backprop did not work, right? So first thing was data on which we are trying to estimate the parameters was several orders of magnitude small. So you really needed millions and millions of data. That's one thing, right? The second point that they figured out was our computers were too slow for the number of iterations that you needed to run. So the number of the compute that you had to do, it's too slow to do that. The third thing that kind of addressed by this layer-wise pre-training was that we did not know where to start searching for the right answer. So remember the box that shall not be named, right? So depending on where the marble starts, it's going to go into different bins, right? In terms of these really deep networks, right? It turned out that where you started influences whether you find an answer or not. Right. So, and we had no clue what's the right way to do it. People are trying all kinds of different ways of initializing the weights. It's not happening. And this layer-wise pre-training, what it was doing was putting the weights in the right ballpark. And therefore, you could learn much more rapidly. So that is one thing that was addressed. But the last thing, we're using the wrong type of nonlinearity. Remember that we had the step function, and then we replaced that with a more gradual function. It turned out that whenever we are using a nonlinearity, that kind of saturates, right? It goes up to 1 and then it doesn't go beyond that, right? As if you have a nonlinearity that saturates, that is what kills the gradient when you're doing backpropagation. So we are thinking that because you are going back so many layers, the gradient was going to 0, but that's because the nonlinearity was squashing. So once people started playing around with different kinds of nonlinearity, that went away. So you could start using backprop to just do any kind of training, right? And finally, we needed better optimization methods. Simple gradient following was not enough. So we needed to come up with better optimization techniques. So all of these things kind of evolved. And Hinton, yet again, the third major thing that Hinton has done, that I'm presenting in my talk, right? So he came up with a bunch of things. So of course, he built this solution on a problem called the ImageNet problem, right? So for people who know what I'm talking about, this is the original AlexNet architecture, which he came up with, which of course, Alex, that EA is Alex, came up with. So they worked on this problem of the ImageNet, right? So there was like 1.2 million high resolution training images, right? So like that, right? So that they had a lot of data. That's the first thing. The second thing they did, which was one of the earliest known implementations in AI, which ran on many different GPUs, right? Multiple GPUs, as opposed to running on one computer. So GPUs are this, the kind of computers that people design specifically to do graphics. So high-speed graphics. So this, you can thank all the game playing that people do for giving money for AI researchers to get to these high-performing computers, right? So because these are originally developed for gaming systems, so that and also all this kind of high-end video editing systems, so that the rendering can be done very quickly. So it started there, right? And so these people, they figured out a way to run these algorithms on multiple GPUs. In fact, this half ran on one GPU, that half ran on another GPU, so they could do things much, much faster than earlier. And the third thing they did is use something called rectified linear units, right? Not linear, that's linear, sorry. Rectified linear units, which basically said, hey, I'm not going to saturate on the positive side. So that's basically the function. So it's the orange one is the one that they tried here, and after that people have done a bunch of things. So now taking away the saturation on both ends, right? So instead of what the sigmoid was doing was saturating on both ends, they took that away, and that again made things work fast. And then they also introduced a lot of new tricks for doing optimization, right? And you can see that all of these things, right? Many of these small tweaks that were done all came from Hinton's group. And there are a whole bunch of other things. There are like 20, 30 papers that I could talk about, which essentially has fed into what the modern thing is. Of course, I'm also talking about Hinton today, right? So you can give me any one of the famous names. I can probably give you 30 papers like this, whatever they have done. So the modern AI is not basically one person's contribution. A lot of people have fed into it. So now you can see what happens, right? So this is the competition that I was talking about, the ImageNet competition, right? So people were actually having error rates of like in the 20s until AlexNet came, and then it dropped. But by now, we started knowing how to train better. So instead of training just 8 layers, people started training hundreds of layers. And so we started getting better and better and better. So in almost anything now you think about, we are doing, have superhuman performance, whether it is computer vision, whether it is speech recognition, right? All of these we are doing better, right? And so it started there, and now we are here. And of course, I know, give me 2 more minutes. I'll flash through my slides. Okay, so all the recent excitement, right? So everybody is happy with like ChatGPT, right? And I know many people, even probably few in the audience, think that AI started in 2012, right? So that's the kind of excitement people have with ChatGPT. But the biggest thing with what ChatGPT did, with OpenAI did, was gave a raw interface to a highly capable AI system, right? So this kind of interface where people can, I mean, of course, Google gave a raw interface to a highly capable search engine, right? People got blown away then. Now you have gotten something very similar, very, very simple interface, right? No controls, no guardrails. You can do whatever your imagination tells you to do with that AI system, right? So that caught people's, imagination. So basically that now you have all kinds of LLM stuff that's going on. And so you can, I'm calling it now as augmenting intelligence now. So you have this, what we call the co-pilot model, right? People are not writing programs in the IT industry anymore the way they were doing before 2012. It's completely changed, right? And now it's going to happen for healthcare. Now it's going to happen in customer support, creativity, and also even search itself, right? Is going to go through this kind of an AI revolution. And the future, you're going to have everything change, right? It's amazing, right? And of course, I just want to tell you that now these models have become super complicated, right? So this generator network alone, right, will put any AlexNet or anything to shame in terms of how large these networks are, right? And likewise, you have another network. Now these two are competing with one another to learn functions. And so it just becomes crazy. And then a lot of, again, diffusion models, which are now being used for generating these images, right? And it's come to a point where, this is a study that was done almost a year, okay, March, right? 40% of people cannot tell if a face is AI generated. So which of this is AI generated? AI? Show of hands. Number 1. How many of you think it's AI? Okay, number 2. Okay, number 3. Number 4. Oh man, the audience is almost like evenly split. Okay, it turns out that this is the only real person. Everything else is AI generated. It's like crazy. I mean, they actually did a proper study on this, and then they found that nearly 40% of people can't tell. It's like crazy, right? And then, of course, I'll skip some of this. So this whole idea of self-supervised learning that we were doing, right, where we are trying to take the input and actually reproducing it in output. We saw that in autoencoders, we saw that in Boltzmann machine and restricted Boltzmann machine and all that. Now people have taken that to extreme limits, right? So talking about now training on the data, not just of a few million images, we're basically training these models on the internet. Right, the entire data that's available on the internet could be text, images, whatever. You're taking all the data and you're training it, and you're producing a lot of complex things, right? And each dabba here is like a few layer neural network, right? It's not like it's like few maybe 30 layer neural network. Each dabba here is going to be something like that, and this put together runs into now the latest version of these models run into trillions of parameters. Not billions. So we were talking so much about so long through the history that we were struggling to train models with a few hundred parameters and thousands of parameters. Now we are at a point in history where we are training models with trillions of parameters, right? And so I'll again not go through this, but you can see what is happening here, right? So I'm going to give you an input. It generates one word in the output, then that word gets fed back in, and that goes and then generates a second word. And then that word gets fed back in, generates a third word, and so on and so forth. And so this is basically called an autoregressive way of operating. And instead of looking at explicit regression, explicit recursion that we had with Hopfield networks and with the Boltzmann machine, this autoregression actually gives you the effect of recursion. You go all the way to the output, get one word, and then you come back and feed the word back into the input. So that basically gives you the way of closing the cycle. So that's what this is like, right? And so of course all of these people have seen, and you can use this kind of next token prediction to do a variety of things. You can ask it to write opinion pieces for you. You can ask it to you can answer questions. Now you can write programs. And there are a lot of these models that are out there, right? And yeah, so I'll skip some of these. And yeah, this always blows my mind. So basically, you can feed in the picture of ingredients to the model and ask it for recipes that uses the ingredients in the picture. Right? So like crazy. So this is where we are at, right? So Arvind Narayanan is a computer scientist from Princeton, and one of the thinkers about what is happening with AI. So he talks about what went wrong with generative AI, because there was huge amounts of hype when this came out, but we are not seeing the delivery as much, because people were able to do proof of concepts, because everybody had access to these models. They could build like tiny toy stuff, but they could not build products that we can go straight to the market. There's a huge gap between building proof of concept and product, and we don't know. So that's basically where we are at. So everybody thinks these models are going to be a huge productivity boost. 96% of industry leaders think AI is going to help them. 47% of their employees say they don't know how to. So I had artificial general intelligence in my title, so I need to have one slide on that, right? So basically, artificial general intelligence is something like this. The intelligence of the system is a measure of its. Okay, let's look at it. The AGI is a system that can efficiently acquire new skills outside of its training data. So I give it a lot of data to look at and learn things, but can you learn things outside the training data? So that's basically it. And we are nowhere close. I don't think we're anywhere close. And all, with due respect to Hinton, all the doomsday scenarios, or at least a decade, 5 decades into the future, maybe longer. And this is, sorry. Oh man, you wouldn't know how you wouldn't believe how the AI hedges its bet. It will not give you a direct answer to the question. You can try that. Okay, it will say no. As an artificial system, I have been programmed to be no, take care of human. Yeah, it won't answer. So it's, I mean, of course, the companies are very worried, right? If say Gemini comes and says yes, tomorrow I'm going to take over the world. I mean, so then somebody is going to go sue Google, right? They're all worried about this. So anyway, so this is I like this. What Terence Tao, the very famous mathematician, right? Terence Tao said, I've been playing around with all of these models. In fact, Terence Tao says the future of mathematics is going to be co-working between AI and humans in proving theorems, right? So he has already started using it. He's writing papers where AI has helped improve theorems, and he talks about how the existing models capacity is like an incompetent grad student. And he believes that maybe in a couple of other iterations, we'll get to a point where we have a complete instrument, okay? Which we will take it, right? Anyway, so my last slide. So Hinton truly has been the godfather of AI. I mean, even though a lot of people have been given that credit. And so I just want to point out, right? So Hinton, from the get-go, believed in this connectionist approach to AI. So when the field went away, right, when nobody was paying attention to Hinton, also he continued to work on this, right? So not once, twice he has managed to revive the field of connectionist AI, right? And so now I strongly believe that AI revolution is here to stay, as we saw with all these examples, right? And but the biggest thing, the caveats that he is giving out, right? It doesn't have to be that you need super intelligence for AI to do harm. Even with the existing AI models, we can do enough harm, right? So we really must learn how to use AI more responsibly. So that's where we are at. Thank you.
Thank you. Okay. On behalf of the library as well as Anurag Center, it's all memento for you, sir.
Thank you.
We now look for questions. We you can ask about Sitabrah and Hinton. To the extent how much you can go ahead with that. But I just wanted to tell, I tried to use AI for this meeting because we announced a small competition for all the, because we have a huge number of emails who have registered everywhere. Then asking about 2 weeks back, we asked them to predict Nobel for this year. In physics, chemistry, as well as this thing. And when I tried myself in ChatGPT as well as Gemini, it first came with Stephen Hopfield. Then it said Albert Einstein. Okay, so this is the kind of answers it was trying to give. And finally, after several layers, few attempts to correct it, it didn't come out with any correct name so far. But it so turned out, since the competition was announced, of course, it was not very popular, didn't go reach all the people. In physics, nobody predicted. And we all, physiology also nobody predicted. In the chemistry, there's one person who predicted it.
Wow.
We are going to give a prize.
Wow.
Next Chemistry Nobel Prize talk will be there on 2nd November. And the person has been asked to come here for receiving the prize. IIT Madras is sponsoring some amount for
Oh, wow. Okay.
That's an interesting part about it. So, and that was a correct prediction also. Name of the speaker.
All three?
Huh?
All three?
No,
Ah.
one person. In makeup.
Oh, okay.
Okay, so that is the one. So that with that I will stop.
That makes sense. So I have one anecdote that I have to share. So after the Nobel Physics Prizes were announced, right? So somebody went to, I'm not sure whether the GPT-4 or Gemini, and actually asked the AI, right? So, hey, what do you think are the chances of Hinton winning the Physics Nobel Prize? And it said 0. He's not a physicist, and these prizes are typically awarded to people who have made contributions in physics. Therefore, there is 0 chance of Hinton.
Good. Okay, anyhow, that is the current status. As he says, things will go far more in future, and we don't know how it will go. So now I will give the floor to the thing. You just raise your hand. Those who want to ask, I will give in certain order to the extent I can see. Because right. Okay, some of them. It's also telling you. Okay, please. Whoever wants to ask, can be brief. Be brief.
Of course. So I wanted to know what the last slide on your presentation was, the cartoon that you wanted to show. So if you have time towards the end, please show us the cartoon.
So you don't read comics, huh?
No, not yours.
Well, I know what his presentation last slide was. Yeah.
So
it's actually from Alan Moore's The Watchmen. You might have seen a
Watchmen.
movie, but this is from the graphic novel. And basically, it's where, Dr. Manhattan, who is this superhuman being, is asked by Ozymandias, if you've seen the movie, you know what it is about, that, he killed a lot of people, but to get world peace. And he asks Dr. Manhattan, it all came out well in the end, isn't it? And so Dr. Manhattan says, the end, it never ends. And then Ozymandias, what do you mean? And Dr. Manhattan vanishes. So basically, it's a, like my take on where is the end? We don't know.
Nice comment. Okay, so my question is, so both of the persons who actually get the physics Nobel this year, their signatories in 23 on probably one of the biggest assault on AI, which was the 2023, request or user citation, whatever it is that was signed by them, saying, please stop giant AI experiments in future. Both of these gentlemen were. So I'm just wondering, and this is probably the strangest prize because the person for the first time, the guy who gets the Nobel Prize, at the announcement, he was connected, was live at the announcement. He says, I regret my decision to, my discovery. So I'm just wondering how much of this is actually a political award, so the governments can bring in big regulations on, stopping AI growth going forward. Because it clearly shows these two gentlemen were against AI being used in the way it is being used right now, and they are signatories on this particular giant anti-giant experiment legislation. So, okay.
Okay, this is not the first time. When Einstein did in area of relativity and E square, etc. He didn't anticipate there would be a bomb. Of course, it was made, and it had a. So all these things have. It's like a sword. How we are going to use it depends on our choice. So you can use it to cut vegetables. You can use it to kill people. So this is an improve. This is kind of a change in science. A development which takes place. How we are going to use, whether it is good or bad, we will see in the future. So it is true. All prizes in Nobel prizes, there is a lot of lobbying going on. It is not only for this, and some even 1 or 2 Indians have also been refused Nobel Prize in spite of great works also because their lobbying powers were probably not sufficient. So this is part of the problem. And we will not get into the politics of Nobel Prize. We will focus on the actual work which has been done. That was the unless you want to say something.
Yeah, I think the question was more about whether this prize is a nod to their opposition to deep AI experiments. But as Ravindran, I'd like to point out, what Ravindran said that, we don't actually need more advanced AI to create harm. I mean, the potential is already there. So this is basically an outcome of emergence, something physicists know. You have very simple elements which interacting together creates properties which are unexpected. And, for people who read Isaac Asimov, those 3 laws of robotics are like axioms. And yet, by playing around with those axioms, you get lots of unexpected features. And there's this short story by Asimov called Thou Shalt Be Mindful of Him, in which he has 2 robots who are put on the shelf, have a discussion about what is human, and come to the conclusion that robots come closer to the definition of humans than humans do, and therefore the laws of, the general laws of robotics does not prevent them from killing humans. So this is an emergent feature, right? So I completely agree with Ravindran that the potential for harm is already there. We don't have to. So I don't really know whether the Nobel Committee was actually thinking of all that. I think they just went to the point where you can't ignore all these developments anymore.
Yeah, I mean, there is all this joke going around about how there are more vocal people than Hinton who against this, right? And they were saying, oh, next they should be giving them the Nobel Peace Prize, like Stuart Russell and folks like that. So, I'm sorry.
Obama has been given.
I'm talking about.
You mentioned Yuval Noah Harari.
Okay, I'm not going to make any comment on that. So going back, I think one of the things that Hinton and a few others, right, are worried about is not humans using AI for harm, right? They are worried about AI becoming quote unquote super intelligence, right? Where they are talking about AI becoming going outside the sentient, right? So that's the kind of things that they are worrying about. And I mean, no, I mean, the kind of stuff that we are doing and the very, very simple tasks, right, at which these AI models can be shown to fail, right? Very, I mean, laughably, right? They're simple like, puzzle, like a 6, 7 year old can solve, and this has no clue, right, what is going to happen. So these kinds of things are still there, right? So to get to a point where we are saying that AI is going to become a sentient being, I think it's a little far off. But given Hinton's investment, emotional and all these years investment into completely believing that the connectionist approach is the right way and we will get to intelligence at the end of it, given the number of parameters that we are talking about, we are really approaching the complexity size of the brain. So he truly probably believes that's going to happen. But with the current technology, that once you scratch the surface and look inside, it just looks kind of laughable, unless there is some significant change that comes out, right? Or Hinton is right and connectionism is all that we need. We don't know.
It's not. It's intelligence, artificial intelligence is
And there is politics for that.
I'm not.
No, I can actually tell you. So there was this two camps back in the day, right? In the 50s, there are two camps that were working on similar problems, right? So one that was headed by this person called Robert Weiner, right? So he had coined the term cybernetics, which is a more appropriate terminology for this kind of stuff that we are doing, right? So the technology that that looks at this thing. And so, but then there's another group of people who are actually against it, like John McCarthy and a whole bunch of other AI scientists who eventually became AI scientists. They were against Weiner for whatever reason, political reasons. So they convened a meeting and then decided to call this field artificial intelligence. It's a misnomer in some extent, but that's politics behind it.
Okay. Yeah. Yes. Good evening. So my question is, it may be very silly or dumb question. So sorry for this. So I can't understand why the AI prize is given in physics category. Like whenever I go and search in Google, they said that they used the tools from physics to build the machine learning things. But I still can't understand what is the relation of physics and AI.
Yeah, it's not a hard question by any means. I mean, there have been very famous people have actually asked the same question. So I'll give you my perspective of it. Okay, I'm sure other people will have other perspectives. Okay, so one has to do with, almost a facetious answer. What constitutes physics? If you consider physics to be, stuff that gets you dozens of physical review letters, yeah, by all practical purposes, physical review letters is the top journal in physics. If that field has generated dozens of papers which were published in physical review letters, by all accounts, I would consider it to be physics. But that's just a facetious answer. I think a deeper answer has to do with the fact that what is it that Hopfield used? So you might say that Hopfield applied the statistical physics techniques, but prior to Hopfield, the tools which it developed were being used to study a system called spin glasses. So what are spin glasses? Like these are magnets where you have magnetic impurities in an otherwise non-magnetic substance. Right? Now, because of the way they interact, some of these connections would be ferromagnetic, some of the connections would be anti-ferromagnetic, and you will produce this frustrated energy landscape which I showed you. But because it didn't have an obvious application, it was just a curiosity. So there were not that many physicists working on this. It was, quite a specialized area. The moment Hopfield showed that, the moment you take a neural network and store more than one pattern, effectively the energy function is that of a spin glass. Overnight, people who knew a bit about this statistical mechanics of spin glasses became overnight experts on neural network theory. And the whole area exploded. So, like you had people doing replica symmetry breaking, you had people doing ultrametricity, which all got, several physical equivalence papers. So people were jumping into this area in droves, and suddenly people started doing discoveries which no one had anticipated. For example, nobody before that had ever asked the question, is there a capacity for the number of memories a neural network can store? You didn't even know, is there a capacity of memory capacity of the brain? Like given these many neurons, how many memories can it store? The question didn't seem answerable. It wasn't quantitative. Now, with spin-class theory, it suddenly became a quantitative answer. Beyond which point, we will no longer have the memory stored as local minimum, local energy minimum of the energy density. And you could basically, Daniel answered that if you store memories which are larger than 14% of the number of neurons, essentially they will stop being local minima and you'd have a completely crazy system. So the fact that you had a complete revolutionization of the statistical mechanics of random magnetic systems happened because Hopfield essentially showed this very intimate connection. Without him doing this connection, it would have continued to remain, somewhat of a, very, very hyper-specialized area, and people wouldn't have really gotten interested into this. But it led to a lot of discoveries in physics. It development of new tools in physics, which allowed him to look at this very specific issues that spin classes generated. So from there, physics has actually learned a lot from, getting physicists into this neural network model. So definitely Hopfield's prize is definitely a prize in physics. Whether deserves a physics prize, well, AI itself has said no. So who am I to say otherwise?
Okay. Okay. Nice. Ah.
I have got one question. I have got one question, which is slightly different from what you have been just talking. Previously, all these things were attributed to the property of mind. Now, all these things are explained in terms of neural network and other things. Is there a connection between brain and the mind as such? Because they are two different categories.
I'm sure Ravindran would have some answer to that.
Oh, yeah, right. But just because you had the mic. No, if I had the mic, I would have said Sitabrah probably knows more about it because he has some neuroscience connection.
No, okay. So, so in the 90s, when I first started my PhD, there used to be this fashion of writing brain/mind. So essentially comes from this, present orthodoxy in the neuroscience community as well as in the, physicists who are interested in neuroscience community, that they are indistinguishable. A brain state is basically what we perceive as mind. So that's the orthodoxy. Now, whether you want to question that, that effectively now boils down to the, probably some philosophy.
Some kind of philosophy.
But, biologically speaking, there seems to be no evidence so far that there is anything to mind other than physico-chemical reactions going on in the brain.
That's all.
Yeah.
Okay, go ahead.
And sir, my question to you is about regarding the reasoning AI, actually. Reasoning AI.
Reasoning AI?
Yes, sir. So still we are lagging, sir, lacking the mathematical model to understand, context and judgment of the data.
Sorry, I didn't quite understand the question. Can you explain?
Still we are lagging, sir, to understand that, judgment and context of the data,
Judgment and context of data?
I'm not sure what it. So, so one of the things, right? So today, both of us spoke about just a very, very, limited aspect of what the work that has happened in AI, right? So if you think about it, in the 50s and 60s when AI started coming up, right? There were a lot of actually psychologists and philosophers who were actually part of the AI community, right? They were actually trying to think about how would you systematize or axiomatize the reasoning that humans do? And there's a whole set of things which Sitabrah alluded to, right? What Minsky and others were doing, this programmatic, the symbolic way of thinking about AI and reasoning and so on and so forth, that necessarily not necessarily stems from reasoning about data. Right? This is reasoning about the thought process itself, and people had tried to axiomatize that. And there are a lot of other work that has happened in terms of large scale search system, logic systems, and inference, and so on and so forth. A lot of work is happening there. And they always go through this cycle, right? So there is some time when the connectionist approach is very popular, and then its popularity goes down, and the symbolic approach picks up, and then after some time that goes down. So somehow we have always been in this either or setting, but now some people are starting to think about neurosymbolic AI, where the reasoning, explicit reasoning component and the AI component would come together. But yeah, right now I think they're just trying to get papers published, not really answer deep questions. We'll come to that eventually.
Well, so Sitabrah, I want to continue with the previous question. So
Mind and brain.
you answered that question as mind is all about physico-chemical processes and all. But in physico-chemical processes, in that sense, involves some kind of quantum thing going on in them. So do we really understand those details? Which and based on that, the actual state of mind and the very defined brain and the mind, the kind of questions he asked and you answered. So
Okay,
yeah.
So your question is like, if I can just paraphrase, you're saying that is there any quantum aspect to brain/mind? Is that the question?
Yes.
Okay, so to the best of our knowledge, there is as of now no evidence that quantum phenomena has any effect whatsoever in the cognitive performance.
Except for Roger Penrose.
Yeah, so Penrose is
That's where I wanted.
Penrose and his collaborator Stuart Hameroff would like to argue otherwise. Which is not to say quantum mechanics has no role to play in biology. There are certain aspects, like for example, photosynthesis, but quantum mechanics does play a role. Okay, when you have interaction between light and matter. Okay, but at least for the brain, there is no experimental evidence as yet that there is actually a connection between any functioning of the brain and quantum phenomena. Quantum phenomena, of course, underlies all of natural processes. The underlying description of any physical system is quantum mechanics. Okay, but that does not mean that we need to know quantum mechanics to cross the road, right? You can say that a car is effectively quantum mechanical. You are quantum mechanical, and so is uncertainty principle going on when you're trying to cross the road. So no, right? Because at some point, the classical limit hits, and at that point, classical physics is sufficient. And so the brain is, to the best of our knowledge now, completely in the classical realm.
The scale of the physics has not gone to the microscopic levels when you want to answer it. More or less classical physics is enough. Okay.
So what's the connection between Hopfield network and physics-informed neural networks?
So in a sentence, I would say that Hopfield allowed you to get a bridge between these systems which call spin glasses or random magnets, for which you can apply statistical physics to understand things like associative memory. Before Hopfield, you had models of neural networks which look very similar. But Hopfield allowed people to see this bridge that you can actually take an energy function, and Hamiltonian, so to say, and effectively equate various features of the brain/mind with a system which is obeying the behavior of an energy of a system associated with energy. So just as you take any particular system, any physical system, and it tries to minimize its free energy, which is this internal energy minus temperature into entropy. Right? So we see that at work in many physical systems. But people naturally have this aversion that this is physics, it's not biology. And so this intuitive separation we always have in our mind about animate and inanimate object kicks in, and you say that any function won't have anything to say about any living system, certainly not the mind. Hopfield showed that at least for certain aspects, like in associative memory, there's actually no difference as to how it operates. And associative memory is effectively acting like a system having a very complex energy function with lots and lots of values, where the valley bottoms, that is the local energy minimas, are actually stored memories. And you can actually explain many aspects of associative memory simply in terms of the energy landscape of that system. So for example, you could argue that what is forgetting? Okay. So from the Hopfield network perspective, forgetting is basically as you put more and more memories into storage, the energy landscape itself is altering. Okay. So as you store other patterns over time, the original energy landscape, when you had certain memories stored as value bottoms, the energy landscape itself is changing. So what was a value bottom before, later is no longer a value bottom, and you basically forget an old memory because you're storing new memories. So, and you could actually experimentally try to do it on a Hopfield network and so on. So this is what I see as Hopfield's great contribution to connecting physics and living systems.
So I think his question was more about this new concept called PINs, so physics-inspired neural networks.
Oh, okay.
You could, So you could think of the Hopfield network as the first PIN, right? The first physics-inspired neural network, because it is actually looking at setting up the configuration of the neural network so that it mimics an energy system. Right, so what people doing now in the modern day physics-inspired neural network is basically set up neural network so that they can simulate other physical systems, right? So they have done this for heat diffusion models. They have actually built a neural network that can simulate heat diffusion. They have built neural networks that can simulate actually motion dynamics and so on and so forth, right? So this basically what you're doing there is bringing your knowledge of physics to impose constraints on the error surface on which you're going to navigate. In this case, Hopfield brought in this energy function. Here, the modern day thing is more like putting constraints on the optimization, putting constraints on the form of the functions you're going to look at, and so on and so forth, and then giving it to the automatic differentiation tools and making sure that you come out with some kind of a gradient activity, right? So that's basically what they're doing. You can think of Hopfield as the first of these, even though it didn't immediately pick up after that.
Okay. So how would we equate the energy value function and the nodal structure of the AI, nodal structure of the artificial intelligence?
What structure of the AI?
Like the energy, Hopkins says that we need to use energy value function, right, sir? Like to.
Okay, so think of it like this. Each brain state, when I say brain, I mean the neural network, can be represented as certain neurons switched on and certain neurons switched off. So if there are n neurons, I could write down what is the state of every neuron from 1 to n. So this I can write it as a binary string, right? So then if there are n neurons, then each of these neurons could be on or off. So there are 2 equals to the power n brain states. Correct? Now the question is, can I associate an energy with each of these states? And Hopfield showed that by just mapping the on and off states with a spin up and spin down description of a Ising model, which is a model for the magnet, you can write down an energy function in exactly the same way that we can write down an energy function for the magnetic system. So by writing down a coupling equation, coupling constant times the orientation of a pair of spins, and then summing over all pairs of spins, you can write down a Hamiltonian energy function. Hopfield showed that by mapping the spin down of a magnet to a neuron being off and spin up with a neuron being on, you can write down an exact energy function which captures the energy of each of these to the 2 raised to the power n brain states. And the Hebb rule gives you a prescription of how to make the memory that you want be a local energy minima. That was the great thing that Hopfield managed to do. By using Hebb rule, he showed that you can design which will be your energy minima. You don't just leave it to chance. Right? So you design the energy landscape. Who is the next one? Okay, go ahead.
Hi, hello sir. So what I wanted to ask was that recently I was reading something on Twitter that some people are testing all the open source models, and there has been something called entropy collapse, which is like all the models due to some instruction fine tuning, because all the models now every company wants to go towards the safety thing. So due to this thing happening of company focusing more on safety and along with that all the innovations. So every model is coming towards a deterministic kind of thing, not going towards being randomized response or things like that. It is going more towards deterministic responses.
Yeah, so I mean, there are a lot of things that are happening that we don't quite have a complete handle on. In fact, very recently, last couple of months, there have been papers that are appearing that have completely thrown away the entire transformer architecture, right? I was showing you the billion parameter architecture and all that, right? They have completely thrown that away and trained a fully connected neural network, which has about 1 trillion parameters. Because of the GPUs and the training methods we have now, you are able to train like a trillion parameter fully connected neural network, and they are showing comparable performance to what some of these GPT models are getting. So now there is I mean, in certain tasks, right? They are not able to train it for everything. So there is a theory going around that says that, hey, it's just the complexity that's induced by the number of parameters in the error surface that matters, and not necessarily the specific architecture that we are using, right? So if that is going to be the case, then what should happen is, as the models become larger and larger, and the same data is being fed to all the models, they should all converge to a similar solution to the problem. So that might happen. But also there is this whole alignment issue that's going on, which is another confusing, confounding factor here. And so people might be aligning to some perceived regulatory structure that is going to come out, and therefore they are getting similar answers. And it's not necessarily a bad thing.
Okay. We have a couple of more questions. If anyone wants, please go and ask the next question. Is there anyone else who wants to ask? It's the last one. Last question, anyone? Okay, this is the last question.
Out of the two, the brain and the mind, which one is
Sorry, which one is?
out of the brain and the mind?
Yeah.
Which one you think fuzzy?
Fuzzy.
Depends on how much you have slept last time.
Really, sir? Really?
Dreaming.
No. I'm just saying, if you're tired, your mind becomes fuzzy. I mean, fuzzy you're talking about in terms of, sorry, fuzzy if you're saying in terms of fuzzy logic and things like that, that's just a mathematical construct, right? In fact, Professor Vidyasagar was like one of the leading control theory person in India, right? He's like amazingly smart person. So he once made a comment that fuzzy theory is probability for people who don't understand probability. So,
Okay.
so I mean, it's just a mathematical context. I mean, I don't know. I mean, whether we represent things actually in a fuzzy form or not, there is no biological evidence for it. And is it easier for us to reason that way? Maybe. But there are a whole lot of other theories that are not quote unquote deterministic, like, or discrete, or like it's not fussy, but still not deterministic. A lot of systems.
In the neurons, singularity. Because it is just a 0 and 1.
Yeah.
Not a sigmoid.
Oh, the neuron. Oh, the biological neuron. Well, McCulloch pits is just one model, right? So, in fact, I mean, our neurons do a whole bunch of different things. There are neurons that are spiking, right? There are neurons that are oscillators in the brain, right? There are so it's not it's like there are different kinds of neurons. It is not like all the neurons are the on-off kind of neurons that we talked about here, right? So that's don't take it too seriously.
One more question. during the time of Spassky and Viswanathan and
Chess, yeah.
Which state at what point you'll remember from the timeline regarding your lectures?
I actually have another timeline where that actually appears, right? That's my personal timeline, because it's slightly funny. So when Deep Blue beat Kasparov, right? So a lot of people in India felt very happy because Anand had beaten the previous version of Deep Blue, and then Deep Blue went and beat Kasparov. And at that point of time, it looked like the only way Anand will beat Kasparov ever. Because he kept losing all the time to Kasparov. Right? So at that point, I said, oh yeah. And then we started noticing all of these things. Yeah. But yeah, it's certainly, see, one of the things you should know, the Deep Blue does not do connectionist learning at all. Everything we talked about today is irrelevant for Deep Blue. The Deep Blue actually uses the whole symbolic reasoning kind of approach for solving the problem. And for problems like chess, right? Where there is a systematic way of thinking through how to get to the problem, and that you can do it in a tractable manner. The classical ways are way better.
Is it more ruley than knowledge-based?
You can solve chess through brute force search, right? Computers used to do it that way, right? Or humans doing it that way? Most likely not. It is just not possible for us to do brute force search at that scale, right? But computers can do that, and they are able to solve, play very good chess. In fact, the current best chess computer, right? No human can beat, because it just basically it plays out before making every move, it plays out the game till the end, all possible variations, and then decides, okay, there's no way I can lose if I play this game, and then it plays. So it's very hard to beat those moves. Huh? Sure, yeah, but AlphaZero also does a lot of rollout. It's not beat another computer. Yeah. I mean, when they play, they often go to draws and things like this. So something like Stockfish, right, which people use quite a bit. AlphaZero beats Stockfish, but then AlphaZero is probably using like 4 times more compute than Stockfish. So no way we can get close to that kind of performance.
More recursions, maybe Hinton may be predicted.
The challenge with recursion is getting it to be numerically stable. That is why autoregressive and other approaches are more preferred. You have anything to say?
Last question. So my question. So I myself, as a blockchain developer, so I've started my.
So I have to say, blockchain has nothing to do with AI. Go on.
So I started learning AI like an year back. So I was experimenting with the RAG and LLM systems. There was one thing which has been going around, as you mentioned about the complexity. There was a debate going between the transformer architecture and the Mamba architecture. There was a discussion going on. The transformer is for the prediction of the sentence. Like, let's say when you're asking AI to write a program, right? So Mamba performs better than the transformer architecture.
Yeah.
So my question is simple. So do you see the timeline where Mamba beats transformers?
I'm not 100% sure about it. In fact, this morning I was having this discussion with my colleague Mitesh about the need to actually go and start looking at the transformer architecture more closely, because a bunch of things that we are facing, right, could potentially be because of the way. We didn't talk about it, but the transformer architecture is extremely simplistic. If one way of thinking about it, the only reason you get this kind of performance, right, is because of the number of parameters you have put in there and the huge volumes of data you're using for training. Right? That's why you're getting some kind of emergent property. So there should be something more cleverer that you can do by looking into the architecture itself. Right? Whether Mamba is the answer, I'm not sure. Right?
Okay, thank you. Now we are at the stage of closing now. Let's thank all the speakers. And request Pitambar to propose the word of thanks. Yes.
I think another long run, very highly, and it's a lot of interest, these topics. In just to make things clear, The keyword here is complex systems. I think complex systems always arouses a lot of interest. We put up on this, and Professor Sinha's last lecture also, everybody was extremely interested. The one that we organized and and all of that. I mean, I have my theory is in the 1950s, they used various parties. So they used various lay analysts, people who had clinics, psychologists who had clinics with no training in psychology. And the reason is everybody has an opinion about the mind. Everybody has some theory underlying the mind. And so naturally, they're very interested in complex systems and things like that. So we want to thank both of you, Sinha, Professor Ranjan. I mean, a great session, and you stayed longer than we had expected and answered everyone's questions. Want to thank the library again for giving us this. And the Science Forum is working around the clock to keep bringing interesting stuff like this to the audience. Hope you enjoyed it. Please, yeah.
We have the